Okay. The odd of an event A is defined to be the ratio of the probability of event A to the probability of the complement of event A here. And so, as we know, the probability of the complement of event A is equal to 1 minus the probability of A. Okay, so that is by proposition 2.4.1, I think. Okay. So once we know the odd, okay, so if we know the odd of A, then PA, so we can say PA is equal to PA complement times the odd of A. Maybe I use ODDA. Okay. All right. And so that, but 1 is equal to the probability of A plus probability of A complement. Okay. So I think all right. Maybe I will change the. So PA complement is equal to 1 over the odd A times P of A. Maybe so I move. Okay, I move a probability of the complement of A to the left hand side and move the odd of A to the right hand side. Okay. All right. So so this is okay, and so that is 1 plus odd A times PA. Okay, and so this is implies that we can compute the probability of the event A, which is just E odd A divided by 1 plus odd A. Okay. Sometimes it is convenient to find the odd of an event A. And so from the odd of an event A, we can compute the probability of event A itself. Now, the odd. Oh, by the way, I forgot. I forgot to put X here. I'm sorry. So the odds of A may change after an evidence is observed. So maybe a new evidence and which is an event E is observed. Okay, so So by Bayes' formula, okay, so the change is that the conditional probability of the event A given a new evidence, okay, divided by the conditional probability of the complement of A given the new evidence. So that is the new odds, okay, after a new evidence. Actually, it's a new event E is observed. Okay, now, and by Bayes' formula, that is would be P of A and P of E given A divided by P of E. Okay, and the denominator is P of A complement times P of E given A complement divided by P of E. Okay, and so we can cancel them. This becomes to P of A divided by P of A complement. So now this is the original odds of event A times the probability of event E given A and divided by event E given A complement. So this is the new, odds of A, and this is the original odds of A. Given E is observed. Okay. So you can see that the new odds increase, right? Increase if this ratio is greater than 1. And this ratio greater than 1 means that the numerator is greater than the denominator, which means that the conditional probability of the event E given A is bigger than the conditional probability of the evidence given not A. So that means that if the evidence is more likely once the event A occur, right? More likely than not A, then that the new odds will increase. All right, so let's say here, so the new odd of event A will increase. Okay, if the event A favors the evidence E and decrease all right, and the new odds of event A decrease if A does not favor the evidence E. All right, so so let's take the example 3.3.I. Okay. Okay, and so here we have an arm here, and we have two type A coin and one type B coin. So there are 3 coins in the arm here. All right, so a random experiment. Right, a coin, right, is randomly chosen from the arm. Okay. Right, so this is this. And the second is that the chosen coin will be flipped. Okay, so first of all, there are 2 actions. The first one is to choose a coin from the arm randomly. The second is that we will flip the chosen coin. Okay, so the coin has 2 faces, head and tail, right? There are 2 faces. Okay, so our random experiment consists of 2 parts. Okay, and so we will let H be the event that it comes up head when flipping the chosen coin, right? And we have a prior information, right? So we have a prior information that the probability to have a head comes up, okay, to have a come up when a type A coin is chosen, right? So this probability is 1/4, and the head shows up when type B coin is chosen. Is 3/4. Okay, so that is the prior information. It depends on the structure of the coin. Okay, so that is a priori information we have. Okay, now a coin is randomly chosen from the arm, so that and meanwhile, in addition, we have probability that a type A coin is chosen, which will be 2/3, right? Because there are 3 coins, and 2 of them is type A coins. Okay, and we select the coin randomly. So we basically assume that the coin can be chosen equality probable. Okay, and the probability type B coin is chosen is 1/3. So they are prior informations we have. Yeah? Okay. Okay, so the first 2 depends on how type A as well as type B coins are manufactured. And so this is the prior information. So now we want to know what is the probability that a type A coin is chosen given that a head comes up, okay, when flip the chosen coin. Okay, so we will want to find it. Okay. All right. And so we think about that our original event A is just a type A coin is chosen. Okay. And we think about the head event to be the evidence event. Okay. So the new odd, the type A coin is chosen given the evidence means that a head comes up when the chosen coin is flipped. And the complement of a type A coin is chosen is just a type B coin is chosen given head. Okay. So a type B coin is chosen. It's just the complement of a type A coin is chosen. Okay. And now, so this is the type A coin is chosen. Probability divided by probability. Type B coin is chosen. Okay. Times a head comes up, right? When a type A coin is chosen, probability of head type B coin is chosen, right? Okay, and now with a prior information, so that would be 2/3, and this is 1/3. Okay, and this one is 1/4. This is 3/4, and so that it would be 2/3. Okay, so this is the new odd. So we have that. And remember, we can compute the probability of the event by using the odds. Okay. So that the probability, the condition probability that a type A coin is chosen given the evidence H, which is the new odds 1 plus new odds. Okay, so this is 2/3, 1 plus 2/3, so that it's 2/5. Okay. Any questions? Okay, now we will generalize the decomposition formula first. All right, so now a collection F1, F2, Fn of n events is said to be a partition of the sample space if they are mutually exclusive and their union is equal to the sample space. So we will say that Fi intersect Fj is equal to the empty set for all I not equal to j, and the union I from 1 to n, Fi is equal to x. And together, this is saying that the disjoint union Fi is equal to S, okay? So by Venn diagram, suppose this is the total event, our sample space X, and this is F1, this is F2, and the last one is Fn. Okay. Okay. Now, suppose we have an event E here. Okay. For any event in the sigma algebra, we know that E intersect with X. So E is equal to E intersect with X. And so now we have a partition of the sample space. So this is the disjoint union Fi here. Now by the distributive law of intersection to union, so we have again disjoint union E intersect Fi. Okay, and look at that here. So this is this part is F1 intersect with E here, right? So that each part will be disjoint. So we have disjoint union, right? Okay, and so by finite additivity, of the probability function, so the probability of E becomes to probability of the disjoint union I from 1 to n E intersects Fi, which is equal to, because this is disjoint union, right? So by the finite additivity, this is equal to the sum of the probability of E intersects Fi. And so this formula, and then finally, by conditional probability, that is probability of Fi times probability, conditional probability of E given Fi. Okay. Again, this is the this is a generalization of the decomposition formula. Okay, and again, we also call this as decomposition formula. Okay. All right, so if the probability of an event E is hard to compute, but the probability of Fi events in the partition are much more easier to compute, as well as that it's easy to compute the conditional probability of event E given event F sub I for each I, right? Then we can apply the decomposition formula, right, to compute the P of E. Okay, so it's a straightforward formula from the original simple decomposition formula. Okay, and so with such a generalization, we have a general base formula. Okay, and so we write this generalization as proposition 3.1 and call it basis formula, right? So suppose we have F1, F2, Fn, a partition of the sample space. Okay, so suppose we have a partition of the sample space. All right, and then for each event E in the sigma algebra, okay, the conditional probability of F sub j given the event E, okay, now which by our definition it's this ratio, right? And which by applying the decomposition formula. So this is equal to P Fi probability of E given Fi. And here, the P of Fj given P of E given Fj. So the proof so it follows from the definition of conditional probability and the generalized decomposition formula. Okay. Questions? So we know this to there, okay, by the the decomposition formula. Okay. And the definition of conditional probability goes to here and here. Okay. Right? Let me make several remarks about this proposition about Bayes formula. First of all, events F1, F2, up Fn are often called possible hypothesis. Since they are mutually exclusive and exhaustive. Okay. Exhaustive means that the union of these n events is equal to the total event. That means that And they are mutually exclusive. So every outcome omega will be in one and only one of the n events. Right? Is that clear? Just like here. If we look at an outcome means an element of the sample space. An outcome can be in one and only one Fi's. Okay, so these events are mutually exclusive and exhaustive. And so they are often called possible hypotheses. Okay. Second, the set of the probabilities of these possible hypotheses, okay, are called a priori probability of the n hypothesis. Okay. So this is quite often to know a priori. Okay. The third point is that the conditional probability of Fi given E, so E may be considered as a new evidence. So given a new evidence E, right, this conditional probability of n hypothesis are called a posterior probability of the n hypothesis given a new evidence E. Okay. Okay. And when we look at the basis formula can be seen as to compute the a posteriori probability of the n hypothesis given the new evidence E. Right? And you can use the a priori probabilities of the n hypothesis, right? As well as the conditional probability of the evidence given individual hypothesis. And usually, this condition probability are quite easy to compute. Okay. Four. Now, after observing an evidence E, we choose a hypothesis Fj, whose a posteriori probability, okay, its maxima, i.e. Fj is equal to the argument of the maxima of Fi, I from 1 to n, such that the Fi given E. Okay, so here is that we compare the posterior probabilities of the n hypothesis given the evidence E, compare them, and find the maxima. Okay, once we find the maxima, we take the argument. All right, so the argument here. So this is the argument, and this argument will be say Fj. Okay, and such a okay, and this is called, so this is called the maxima a posteriori. We call MAP, decision rule, because we want to decide which hypothesis, okay, is the one you want to choose. Okay, so let's take an example. 3 by 3 point n. All right, suppose that the random experiments is that okay. First of all, to choose to select a flashlight randomly from a bin containing one hundred flashlight, where 20% are type 1, 30% type 2, and 50% tab 3. Right, so first of all, there is a bin. Okay, in this bin, there are 100 flashlights. Okay, and 20 of them. Tab 1, 30 of them. Tab 2, 50 of them. Tab 3. Okay, and then we will say that the probability maybe I just, and apply information okay, the probability that tab 1, 2, or 3 flashlight will give over 100 hours of use is 0.7, 0.4, or 0.3 respectively. I.e., by letting E to be the event that flashlight give over 100 hours use of use. Okay. So by letting this event, the continual probability of tab 1, right, it's equal to 0.7. The conditional probability of tab 2. So, okay. So we will have hypothesis 1. It's tab 1 flashlight is chosen. Is selected. Okay, it's selected. H2, H3. Okay, so we have 3 hypotheses, right? Hypothesis 1, tab 1 flashlight is selected. Hypothesis 2, tab 2 flashlight is selected, etc. Okay, so with this event defined, so we have probability of E given hypothesis 1 is 0.7. Probability of E is that a flashlight gives over 100 hours of use. And the probability of it given as 3. Okay, and in addition, we have that the a priori probability x 0.2, 0.3, 0.5. Okay, because in that beam, there are 20% of first light to be type 1, 30% type 2, and 50% type 3. Okay? All right, so the a priori, this is called the a priori probability. The three hypotheses. Okay, so if there is no other evidence, if you draw, if select just randomly from the beam, okay, take out a flash fly, and when you make a decision, right? When you want to make a decision, which types of flash fly you selected them, then you will decide to say type 3, right? Because it is the most probable type you can have, right? So that if this is a gambling, for example, you bet $10, okay, and if the decision is correct, then you will gain $10. But if the decision is wrong, you will lose $10. So what kind of hypothesis you will decide? Without other information, just a prior information. I think the most reasonable decision would be type 3, right? We all agree with that. But how about if we know after some test by some instrument, the selected, so what is the posterior probability of probabilities of the three hypotheses after the evidence is observed. So you pick up a flashlight and put into an instrument. The instrument tells you that, wow, this selected flashlight give over 100 hours of use. So you can wait, right? So you select a flashlight and turn it on. After 100 hours, how many days? 4 days, right? Then you know, okay, it's over. So you have this evidence. So now you will change given this evidence, so what? So that you have to compute Right? So your decision should base on the new evidence, because now you have information. Okay, so you compute this is 3 probability. right? And the decision you make should be the one such that a posterior probability is the maximum. So that you should make the MAP decision here. The maximum a posteriori decision. After you gain you have this evidence. Okay. Okay, so now by Bayes formula, now we can compute the a posteriori probabilities. All right. So now we have probability of H1, probability of evidence given H1. And the denominator would be probability of H1, probability of E given H1, plus probability of H2, given probability of E H2, plus probability of H3, probability of E given H3. Okay. And this is, what is that? Hypothesis. So now we have a prior, this is 0.7, and 0.2, and 7, okay? And here is 0.2 times 0.7 plus 0.3 times 0.4 plus 0.5 times 0.3. Okay. And so the final, let me write it down. So that would be 0.14, 0.41. So this is 14 over 41. Okay, and you can compute that this is pH2 and pHE given H2, and this is PE. And we know 0.41 is PE, right? And this is 0.3 times 0.4. So this is 12 over 41. And this one, and this is pH3, E given H3, PE. Okay, and this is 0.41, 0.5 times 0.3. So this is 15 and 41. And once again, when you compare these three numbers, the MAP decision is type 3, once again. Even though they become to be more comparable, 14, 12, and 15, but this one is still the largest. Okay. Right, and this kind of running experiment has been done daily in police stations, especially the bureau of the police investigation. Because you can think about that the hypotheses are suspects, right? So they may have 3 suspects, suspect 1, 2, and 3. And then according to their criminal record, they will have a prior probability to make a certain crime, right? So that is the prior probability. Without any evidence, the the policeman will track the most likely person to make a good crime according to the a priori probability. But all the detectives will try to get more evidence. For example, maybe suspect number 1 committed a heavy crime before, but for this certain crime, this suspect went abroad, so it is an evidence of absence, and so the likelihood would dramatically lower, right, reduced, because of this new evidence. Okay, so if the policeman has more and more evidence, then the a posteriori probability will change for the 3 suspects. Okay, so if the detectives can collect more and more evidence, then the final charge or the final MAP decision will be correct in high probability. Okay. Okay, so but as we know, this is still in the investigation period, right? Okay, not go to the prosecutor's office, because for a prosecutor, the prosecutor asks for 100% correctness. Okay, so this decision process is to decide the resource for the police station to dispute 2 different suspects. If a suspect has more likely to commit a certain crime, then the police station will put more resources, like more policemen to tracking this suspect and to gather more evidence from this suspect. Okay, right. So this is if you watched CSI movies before, right? or TV series, they have done a lot of things like that. Okay, so evidence are very important, and based on evidence, you need to compute a posterior probabilities, and based on the posterior probability, you make MAP decisions. Okay. Any questions? So even though this is a simple example, but the scenario apply many disciplines, okay, in humanities, social science, as well as economics, and also in communication engineering. Okay. Okay, so if no question, then let's take a break for 5 minutes to 2:30. Okay. Now, so we discussed the concept of conditional probability a lot. Now we will go to the concept of independence. Okay. Right, so we will talk about independent events. Okay. Now we give a definition of independence. So two events, E and F, okay, are called, sometimes we say statistically independent of each other. All right, if the probability of their intersection is equal to the product of the probability of E and the probability of F. So this is a definition. And sometimes we state statistical independence because in linear algebra or nonlinear independence before, right? So they are two different concepts. Okay. So in the context of probability theory, independence means statistical independence. Okay. So independence is given. This concept is given by definition, just like the concept of conditional probability is given by definition. Okay, but this both concept becomes intrinsically important. Okay, when we developed our theory. Okay, so to develop, so this is the very basic formulation of independence events, okay, for two events. Okay, yeah. So now, let me give me a remark. If we have a probability, we have an event F with zero probability. Okay, so if we have this fact, right? Then F is independent of any other event, E in F. Why is the reason? Since the reason is when it's here, since the intersection of E and F is a subset of F, so that okay, so this is from axiom number 1. This is from proposition 2.4.2, sorry. Okay. Okay, so by the sandwich lemma, 0, 0, so this implies that the probability of the intersection of E and F is equal to 0 too. Right? So that 0 is equal to probability equal to 0 times probability of probability of E times 0, right? No matter what is the probability of E, and this is the probability of E times probability of F. Okay, and so meet our requirement here in that definition. Okay, so once you have an event F which has 0 probability, then this event is independent of any other event. Okay, that's the definition here. All right, let me address 2 additional or extra proposition. All right, so proposition 3.4.a, if E and F, okay, are 2 independent events, all right, then the conditional probability of E given F is equal to the unconditional probability of event E, and the conditional probability of event F given event E is equal to the unconditional event of F. So this proposition connects the concept of conditional probability and the concept of independence together. Okay, together. So and the proof is quite simple. Right? So if by definition okay, so of course, so this is done. If the probability of F is not equal to 0, then we know that PE F is equal to P probability of E intersect F divided by probability F. Okay, but because E and F are 2 independent events, so the probability of the intersection of E and F is equal to the product of PE and PF. This is PF, and you cancel them, so you get PE. Again, you get this one. All right? And by symmetry, we have the same result for probability of F given E. Okay? So the proof is quite easy here. By the way, any questions? You always remember when you want to put something in the denominator, you have to make sure that this denominator is not 0. Okay, otherwise you will commit some simple logical error. you should learn in primary school, right? Okay, the second supplementary proposition (3.4.b), if either the conditional probability, if either one this conditional probability of E given F equal to the unconditional probability of E, either, or the conditional probability of F given E is equal to the unconditional probability of F. Either one. Not necessarily both of them, but just either one. Okay? Then E and F are independent of each other. So this proposition is the converse of this proposition. Okay. All right. So assume that we have this identity okay. If probability of F is equal to 0, then of course E and F are independent. By the above remark. Right? We make a remark before here. So if of course this must be true. Now if the probability is non-zero, then PE equal to P E given F by definition. So now we are able to put the probability of F in the denominator because it is non-zero. Okay, and so when we move the P of F to the left-hand side, so we have and we have done. Okay. So again. Okay. Now the first proposition in the textbook is that if E and F are independent, then E and F complement are also independent. Okay, so now we prove. Before I give a formal proof, we can think about that. This is quite reasonable, right? Because it says that E and F are independent to each other. Okay, so that by our previous propositions A and B, that given F, right, the conditional probability of E is equal to the unconditional probability of E. Okay, so that if given not F, because F, the complement is not F, right? The information will be symmetric. So given F complement, the conditional probability of E is equal to the unconditional probability of E. Okay, and once again, by this one, E and F complement is independent of each other. Okay, so the reasoning, you can use propositions 3.4.A and the proposition 3.4.B as the bridges, right, to get over to this conclusion. But here I can give you some numerical justification. Okay, all right. So here is that proposition is equal to, so by the, anyway, by the decomposition, is that okay? Things disjoint union, okay, by decomposition, and by the finite additivity of the probability function, okay, so that this is the sum. And because E and F are independent, so this is PE, PF plus P intersect FC. Okay? Now, right? So you move this term to the left-hand side, and we will have, so this is PE minus PE, PF. So now the common factor, okay, and by proposition 2.4.1, this is the probability of F complement. And now we prove that the probability of the intersection of E and F complement is equal to the product of the probability of E and the probability of F complement. Okay, so the E and is independent. Okay, so this is done. So we can verify it, right? We can prove it numerically just by the computation here. Okay. But I ask you to think about have an argument through the proposition 3.4.A and 3.4.B. Okay. Right. Now corollary 3.4.C, supplemental corollary. If E and F are independent of each other, then so do E and complement. Why? Well, E and F are independent of each other. Implies E and FC are independent of each other. Okay, now we switch these two. So FC and E are independent of each other. And so FC and EC, now this is fixed, right? And now we take the complement of E, independent of each other. So we have and the other, by symmetry, we know EC and F are also in. Okay. So now you can see so the remark is that so remark. So if E and F so as a summary, if E1 and E2 are independent of each other, then B1 and B2 are independent of each other. Where B1 is equal to E1, our E1 complement. And B2 can be E2, our E2 complement. Okay? All right, so this is a summary for proposition 3.4.1 as well as corollary 3.4.c, right? So B1 can be E1, our E1 complement. B2 can be E2, our E2 complement. Whatever you choose, then B1 and B2 are independent of each other. The second remark, I'm sorry, I make two remarks too. The second one is that if E is independent of F and is also independent of G. Our question is that it is independent of F intersect G, right? And so E is independent of F. and E is also independent of G. Our question is that is E independent of F intersect G? The answer is no. So please see example 3.4.E. Okay. So now, up to now, we discussed independence of two events. Now we try to generalize the concept. Okay. So first of all, three events, right? E, F, and G are called independent of each other if the probability of the intersection of E and F is a product of probability of E and probability of F. All right? And similarly, for the other two cases, all right? So this is a pairwise situation. But we are talking about independent of each other, so we talk about the three events together. We say that these three events are independent of each other. So pairwise independence is not enough. Actually, we have an additional requirement that the intersection of these three events should be equal to the product of their respective probability. Okay, so we have for three events, the concept becomes require not only the pairwise independence, but also the last one, okay? The last one here. The last one is very important. Why? Let's see. If E, F, and G are independent, then E is independent of any event, right, formed from F and G. For example, okay, let's say E is independent of E, F union G. Right? F union G is one possible event formed from F and G. There are many others, right? For example, F intersects G, F complement union G, F complement intersects G. Right? So you can do logical combinations by using and or not, right? We have three possible logical operators and or not. Okay? So E is independent of this. All right, now we prove that for this special case. So the reason is here. Probability of E intersect F union G. All right. Now, by the distribution law of intersect to the union, so this is E intersects F union E intersection G. Okay. All right. And so by the inclusion-exclusion formula, right? This is 1 and 2, E1, E2. So PE1 plus PE2 minus PE1 intersect E2. But these two, the intersection of these two is E intersects F intersects G. Okay, so this is from inclusion-exclusion formula. All right. Now, because E of G are independent, so the probability of this intersection is okay. Is that okay? Okay, so we just plug the formula here. And so they have common factors. Okay, so they have common factors here. Now, again, by the formula, because they are pairwise independent, so this is minus P F intersects G here. Now again, by inclusion-exclusion formula, so this is probability of F union G. Okay, and we have done. Because we prove that the intersection of E and this union has probability which is equal to the probability of E and probability of this union. Okay, so E is independent of the union of F and E, G. All right, so that is an example. Now you may ask me, can I prove that E is independent of any event formed from E, F, and G, all right? Without enumerating all possible events formed from F and G. Yes, we can do that, but that will take some time to do so. Okay, so I decided not to do that. Okay, I just state the statement here and give this example. All right. If you are interested, you can take another example to try. All right. At the end of the semester, if you still are interested on this result and ask me a proof, well, tell me. I will send you a note. Okay. Later on. Okay. Because a proof is not a big deal, but of course that is a big deal from regularity. But I think I would like to go through fundamental concept in the theory of probability as quick as possible. Especially, we are in a short semester term, right? We have only 16 weeks only. Okay. All right. So that I just make the statement here and provided only one example for justification, but we can do proof for that. Okay. Questions? Okay. So wow. Okay. I have behind the schedule anyway, but well. Questions? Okay. So next week. No, I'm sorry. On Thursday, I will generalize the concept independence to a finite number of, say, n events, and to a collection of infinitely many events. All right, later on. Okay. And by the way, I have to remind you that the coming Saturday we will have a pre-makeup lecture in the same time slot, Saturday. Okay, March 5th. Remember that. All right. So I'll stop here and see you on Thursday.